Love you if you see Riemann sum over here. This is a problem from Soviet Union University Student Mathematical Olympiad 1976. Okay, so let's try to do it. Um, Limit from n equals n to infinity, and then we have sum from I equals to 1 to n to the power I by n plus 1 by I. Yeah, and then let's take n common out. Limit n goes to infinity and 1 by n, sum from I equals to 1 to n to the power I by n, 1 plus 1 by in. Okay, wait. For Riemann sum, like we would basically most of the time search for this expression. Yeah, 1 by n, sum from I equals to 1 to n of f of I by n, isn't it? And then if there's this expression, we will say this as integral from 0 to 1 of f of x dx, isn't it? But here, we don't really find that, do we? No, there's not. This is not a function f of I by n. So what do we do? Okay, so for that, you need to expand your definition of Riemann sum. Yeah. So most of the time, how we define Riemann sum is just there are just two expressions, basically integral from a to b of f of x dx as limit n goes to infinity, sum from n equals to 1 to infinity f of a plus b minus a by n times I, b minus a by n, or the other one is integral from a to b f of x dx of limit n goes to infinity, sum from not in okay sorry, here's a mistake. I goes from 1 to n, I goes from 1 to n, I goes from 0 to n minus 1 f of a plus b minus a by n I, and then b minus a by n. We just most of the time define the integral using the Riemann sum in these two ways, but these are not the only ways, and this is not really the absolutely correct way to define it. Let me show you how graphically there are other better ways to. So basically, let's see what this sum gives us. First of all, let me draw a Cartesian coordinate system. Let's say graph, argand plane, and let this be a function f of x, and let there be a, let there be a, and let there be. Say that there are some n subdivisions, and that's why each of them is basically just b minus a by n. Yeah, this distance b minus a by n. So the first coordinate is a plus b minus a by n, a plus b minus a by n times 2, a plus b minus a by n times 3. Yeah, so that's how these coordinates work. And now, okay, so first of all we have a plus b minus a by n times 1. Yeah, so this point, and f of this point is this value, this height, and this height times this gap. So firstly we get this area, isn't it? When I equals to 1, we get this area. Now when I equals to 2, we get a plus b minus by n times 2 is this point, and corresponding functional value is this, and gap is this over here. So we get this area. Yeah. Again, the other one gives this area, the other one gives this area, the other gives this area. That's slightly incorrect. Yeah, this area, and then this one. Okay, so basically now as the n increases, this becomes smaller, and this approaches the actual area. Yeah, now basically what you can see over here is this definition only considers the height from the right endpoint, just the height from the right endpoint. Yeah, and now this definition, how, let's see how the other definition works. Yeah, the function a b and there are n subdivisions, and this width is b minus a by n. Yeah. And the firstly we have height when I equals to 0, so that we have f of a times this division. So the first area we get is something like this one. And now the next area is when I is 1, so corresponding to this we have this height. Second area is this thing, and the third area is this. So the other sum like works like this, it finds the sum of these areas. But when n goes to infinity, like these also actually correspond to the actual area of the under curve, though. Yeah, but when n's not infinity, the area approximated by second Riemann sum is less than the actual area, whereas from this is greater than the actual area. Yeah. So now this involves the left endpoint heights. Yeah, left endpoint heights. Yeah. And this involves right endpoint side. Yeah. So since when n goes to infinity, this is so small, so that's why it doesn't really matter. Yeah. And not just these, we can also consider any point in between these two. Yeah, in between this let's say the one of the point is, let's say a plus b minus a by n I 2, and the other one a plus b minus a by n times I plus 1. Yeah, even if like we have these two gaps, and like there's some any like a random point, let's say chi of I, that belongs in this region, instead of like either the right endpoint, left endpoint value or right endpoint value, we can also like choose any point in this gap, in this like from a plus b minus a by n times I to a plus b minus a by n times I plus 1. In this region, we can take any point like chi of I and still take its height. So basically, like, graphically, let's see, and that will be clear. Function a b. Yeah. And there are subdivisions. Yeah, basically let's say we take like chi of 1, chi of 2, chi of 3, chi of I. Yeah, so on. Corresponding to this, we can take the height and then find the area. We can do this as well. We can take the height and then find area. So we can work on we can work this way as well. You understand? And also this will give you the Riemann area if the width is so small. Yeah, that's why I can also define this in a different way. So the new definition is, if chi of I belongs to a plus b minus a by n I to a plus b minus a by n times I plus 1. Yeah, basically these two points are also belong in this point, so these are also some special case of chi of I values. Yeah, or let's say if there are any other points in between them, even in such cases, using that chi of I, we can define the Riemann sum, basically integral from a to b of f of x dx. Then we can write it as limit as tends to infinity, sum from I equals to 1 to n f of chi of I that belongs in between these two, and then b minus a by n, the gap. Okay, this is also like generalized Riemann sum that covers both the cases and also some of the new cases. So in this problem, what we will basically try to do is yeah. So basically, in this problem, we will have a chi of I that lies between I by n, let's say I minus 1 by n to I by n. Yeah, such that the chi of I value will be 2 to the power 1 by n plus I by n plus, not n plus. You will understand. I will just wait some time for me to make the scenario. Plus 1 by in in our function. uh, okay, so no, okay, I'm sorry, no, not this. So there will be such things such that 2 to the power chi of I will be this value. Do you get me? So what I'm trying to say is, uh, for this series as well, like in between uh, I minus 1 by n to I by n. So basically, if like b be 1 and a be 0, so in this gap, like there will exist some chi of I values, such that 2 to the power chi of I will just always be this value. Yeah, if you have to try see it from a graph, if you want to see it from a graph, what I mean. So basically, let's say if we have a function f of x, and then this is let's say 2 to the power x function. What I will do is, I will show that, first of all I will show that 2 to the power I by n by 1 plus 1 by in, this will be less than 2 to the power I by n, and greater than 2 to the power I minus 1 by n. I will first show this for I greater than 2, that will be true. Yeah, and then after showing this, let's say if we, there is 0, there is 1, yeah, and there are subdivisions being made, yeah, and let's say this is just 1 by n, 2 by n, 3 by n, and there are such things. Now if I prove that this value actually lies in between 2 to the power I minus 1 by n and 2 to the power I by n, yeah. So basically, let's say if I is 2, then if I prove that this value like always lies between, let's say this is 2 to the power I minus 1 by n. Now for this case, this is the 2 to the power 2 minus 1 by n, and this is 2 to the power 2 by n, yeah. Now if I always prove that like this value is always over here, such that there is a chi of I, yeah, not just for these, also for 2 and 3. If this is 2 to the power 2 by n, this is 2 to the power 3 by n. Now 2 to the power 3 by n by 1 plus 1 by this 3 times n. So this value will always be between this. There will always be chi of 2, such that height this value will be here. Again, for the other term also, this height will be in between of these two, so that there will exist a chi. So if I prove that this value will always lie between these two heights, yeah, then like there should exist some chi of n corresponding to this height that will give this value. So basically what I can now say is, there exists a chi of I such that it will be such that like chi of I lies between I minus 1 by n to I of n, and this will be equals to 2 to the power I by n by 1 plus 1 by in, yeah. So if I like prove this expression, that tells me that there will be a chi of I such that 2 to the power chi of I will be this value. And why? By intermediate value theorem, like because the function is there, like, and there are between two values there are two heights, yeah, and if the height lies between these two values, yeah, and if it is continuous, and obviously there should exist some point in between them, so that the height will be always in between these two, yeah. So that's why we can say there's a chi exists. Now after saying that, like I will try to use Riemann sum, but first of all let's prove this expression. How do we do that? So we basically have to prove that 2 to the power I by n by 1 plus 1 by in is less than 2 to the power I by n is greater than 2 to the power I minus 1 by n. And now this is, for this to be true, like I should be greater than 2, yeah. It doesn't hold really for when I is 1, but that will not matter, because like there are like because this is an infinite sum where I goes from like 2 to infinity, so the sum will not really, like it really doesn't matter like if one of the case is escaped. Now let's try to prove this. This is simpler because this is a positive value greater than 1, so of course that's why this will be lesser than the other expression. But and to prove this, like we will use some techniques. Yeah. Now this is equal to 2 to the power I minus 1 by n times 2 to the power 1 by n by 1 plus 1 by in. Yeah. Now this is also equals to, I will like involve e over here so that like there will be some ideas. E to the power ln 2 by n by 1 plus 1 by in. Now there's an inequality involving either e to the power x greater than 1 plus x if x is positive. So using this is greater than 2 to the power I minus 1 by n. This is 1 plus ln 2 by n by 1 plus 1 by I by n. Now for this to be greater than 2 to the power I minus 1 by n, basically this thing over here, that this needs to be positive, and for that ln 2 should be greater than 1 by I, yeah, because n and same, 1 and same. So ln 2 basically needs to be greater than 1 by I. And now when does that happen? ln 2 is basically 0.69, yeah. And if I is 1, then it's not greater than 1, but I is 2, then this expression is 0.5, 0.33. So that's why when I is greater than equals to 2, this inequality holds. Yeah, so that is proved. Now for I is greater than equals to 2, this holds, and for I equals 1, that doesn't hold. So that means like we will not be able to like find epsilon in the first case when I is 1, yeah. But that will not really matter, because even if the one small rectangles is like just ignored, the other sum will give us the exact value. So now after we have like proved all of these facts that these lies in between, yeah. So what we have proved till now, that yeah, this value lies in between 2 to the power I by n by 2 to the power I minus 1 by n. That's why by intermediate value theorem, if a chi of I lies in between these values, we'll have such chi to the power chi I, then that will be equal to this value. Now if we have this, what can we do? Now we can take basically Riemann sum. Okay, so basically sum from I equals to 1 to infinity, yeah, basically from 2 to infinity, 2 to the power chi of I, yeah, that is this exact value. No, not that value. So this is okay. Okay, let me write it over here. So now we can write this as limit n tends to infinity 1 by n sum from I equals to 1 to n 2 to the power chi of I, yeah. So that chi of I lies between I minus 1 by n to I of n, I by n, yeah. And then like now this can be written as okay, this is from 2 on, not 1. Anyways, like 1 will go to 0. Okay, basically it doesn't matter. Now we can write this as integral from 0 to 1 of 2 to the power x dx, yeah. And so this is 2 to the power x by ln 2 from 0 to 1, and that is 2 minus 1 by ln 2, that's 1 by ln 2. That's the answer. Now like I do think that my explanation made sense, cause I don't know like how better I was able to explain, but I do hope you got the things, yeah. If not, you can comment down like where did you have the confusion. I hope the explanation was clear and hope you enjoyed the video. Thanks for watching, and yeah, let me write the answer over here in case you skipped and are checking for answer right now. 1 by ln 2. This is it. Thanks for watching and look forward to seeing you in the upcoming videos too.